SwayamPrabha. Digital India. Educated India.
So, what you see that the development of boundary layer on a solid wall in one sense supports the assumption of inviscid irrotational flow, that over the large part or over almost the entire flow domain, the flow is basically inviscid irrotational. However, it says that there is a very thin region where the effect of viscosity cannot be neglected, whatever high the Reynolds number may be. Whatever high the Reynolds number may be, there will be an extremely thin region where the effect of all these effects, the effect of no slip boundary condition, the effect of vorticity, the effect of viscosity, they cannot be neglected over a very thin region. And it suggests that this thin region must be solved separately. This is an extremely thin region, but this must be solved. This cannot be completely ignored. What we did earlier, this cannot be completely ignored. This has to be matched or added with that earlier solution that we are discussing about, the inviscid irrotational flow. However, the very nature of boundary layer helps us in simplifying the flow equation to some extent. It will not be as simple as the inviscid irrotational flow equation, but it will still help to simplify to some extent. This comes from the fact that in the normal direction, the normal to the wall, in that direction, the changes occur over a very small distance, over the thickness of the boundary layer. We of course do not exactly know what is the thickness of this boundary layer, or whether we will be even be able to define exactly a thickness of the boundary layer. We simply know that it is of the order of inverse square root of Reynolds number in general. But see, these are in a real situation, in a practical flow situation, there is no two different region, it is just only one flow. This is our mathematical nature, that description, that near the wall there is a region where velocity gradients are occurring very quickly, velocity changing very quickly, and after that it is not changing. But in the real case there is no discontinuity, it is a continuous flow from the solid wall to infinity, it is a continuous flow. Within that continuous infinite region, we have separated one thin region and one the remaining part. Say one is say about 0.01% and the remaining is 99.99%. But those two are not two distinct identity, that you must remember. Basically, that is a one flow with some distinctive properties, and we are making them two different flow, but in reality they are not two different flow, only one flow. Anyway, now along the normal direction the changes are very rapid, the velocity changing from 0 to the characteristic velocity, or what would have been the inviscid flow velocity over a small distance, while in the streamwise direction or in the flow direction the changes are occurring. In the streamwise direction also the change in velocity is of the order of u infinity, that you have seen. The change in velocity in the streamwise direction is also of the order of u infinity. We have seen the maximum velocity can reaches 2 times or 3 times, minimum velocity may become 0. stagnation point. So, the change is of the order of u, but this characteristic change is taking place over a larger distance L, while in the normal direction or in the direction of the boundary layer thickness, the change is taking place over a small distance. So, the gradients are much larger in the normal direction or y direction. Okay. So, see, this is that length earlier what we were considering characteristic length. Now, we should consider when we discuss only about the boundary layer, we should consider two characteristic length, one along the streamwise direction which is of the order of the body size, and a characteristic length in the within the boundary layer. For the boundary layer, we cannot take that body length as the characteristic length, because the boundary layer is much thinner than the body length, much smaller compared to the body length, boundary layer thickness. So, we need to consider a separate characteristic distance in the for the boundary layer. Now, boundary layer hypothesis, what it implies, as you have said, that the gradient in the x direction or the streamwise direction sorry. Now, let us consider each of the equations separately. First, consider the x component of the momentum equation. Can anyone tell what is the x component of momentum equation? X momentum equation. Anyone remember x momentum equation? We will consider 2 dimension, not 3 dimension. du dt plus u du dx plus v du dy equal to minus 1 by rho dp dx plus nu into d2u dx2 . That is, let us consider this flow over a flat plate, because almost all aerodynamical bodies are approximately flat plate. So, we will consider a flat plate of infinite width, body of infinite width, 0 thickness, and in the streamwise direction, let us say length be L. And essentially we are considering only this part of the flow. Okay. And remember what we are showing here, this edge of the boundary layer or the boundary layer, that is basically a pseudo boundary. There is practically no such interface in the fluid. It is a continuous region of fluid. If we look to that flow, however closely, we will not be able to see this type of interface. This is just a mathematical artifact. So distinct means, see, you can't see it that there is some layer like this. That is what I said, that is a continuous region of flow.
No, the velocities in that layer.
That boundary, if you measure the velocity,
will it be a distinct jump from this?
Not distinct jump, it is no longer a jump, it is a continuous variation, smooth variation. The velocity variation, or what is known as the velocity profile, see, the velocity will vary, later on you will see it. If we call this is that distance y and this is the velocity u, within the boundary layer the velocity will vary something like this, it may be something like this, or it may be something like this way it will go on, a smooth variation, no jump. The jump was at t equal to 0 only. Now, you see this, what essentially we can do from this equation based on the boundary layer hypothesis, that d2u dx2, which is much smaller than d2u dy2, can be neglected, because this is much smaller compared to this, that is what the boundary layer hypothesis says. So, we can remove this from the term. Now, one more thing, see normal component of velocity v, we can intuitively say the original flow was in this direction, the free stream was in this direction, u infinity we took, no? So, u infinity and knowing the nature of this geometry, what we can see is the velocity here is predominantly in the x direction, there might be a very small component of normal direction. If the flow would have been a purely inviscid flow, will there be any normal component of velocity in this situation? No. You can look back to our solution of our flow over a flat plate, which we obtained the analytic solution by Joukowski's theorem, flow over a flat plate. You can see that for the inviscid flow, the v component of the velocity on is 0, and that is also from your observation or practical experience also you can see that if you have a flat plate and the flow is along that direction, then the flow will be only in the x direction. There might be some small values in the y direction here within the boundary layer because of viscous action. So, one thing is known that the v is very small, the v component is also very small. Now, let us come back to the continuity equation for two dimensional continuity equation. Okay. We are considering incompressible flow. So, the two dimensional continuity equation is simply du dx plus dv dy. Now, what this equation suggests? That these two terms have same size, because they add to 0, the two terms add to 0. So, their magnitude is same. Their magnitude is same. And what is the order of magnitude of say du dx? U by L. Okay. So, in this and dv dy as we can say is a v by delta. Now, if they are have to be the same, let us say u by L is of the order of 1, let us say that u by L is what we call 1, then v by delta should also be of the order of 1 or v will be of the size of delta. Of course, remember we are saying of the size of same two different quantity v and delta. So, v cannot be delta, do not write equal, v cannot be equal to delta, v is a velocity and delta is a length. So, these two quantity can never be same. A velocity may be 2 meter per second or length may be 2 meter, but they are not same still. So, never write v equal to delta, remember even if their values are same. So, whatever is the order of du dx, we have the same order of dv dy. or we should have written it other way, order of smallness of V is same as that of, should have been other way, order of smallness of V is same as that of delta. So, that delta is of the order of inverse square root of Reynolds number. So, V will also be of the order of inverse square root of Reynolds number, the magnitude. Isn't it? Or you can write that delta is L, delta is proportional to L by square root of Reynolds number, and V is proportional to u infinity by square root of Reynolds number. Now, with this, look back to the x momentum equation once again. Look back to the x component of momentum equation, x momentum. Can we make any further simplification? Oh, sorry, not. Can we make any further simplification? Du dt plus can we make any further simplification here? Can it be neglected? Can it be neglected? Yes. Will it be of smaller order? We already had du dy much larger than du dx. This we already have. Now, compare these two terms. Cannot be neglected? It cannot be neglected. So, no further simplification. So, okay, no further simplification. Now, let us come to the y momentum equation. Y momentum equation. Think for order of magnitude of each of this term and then say which pressure, of course, we do not know anything. So, we will not make any. We already have order of u is u infinity, order of x L, order of v is u infinity, order of u infinity r e to the power minus half, order of y also u infinity r e to the power minus half. Looking that, what will be the order of each of these term? Time term also forget. Okay, what is the order of this equation in terms of Reynolds number? Huh?
U infinity squared by root r e into L.
Okay, u infinity square by L into r e to the power minus half. Okay, what about the second one? Same.
R e won't be minus 1, r will be minus 1.
So, it is u infinity
Squared r e
by L into r e to the power minus 1. Okay. Here the first one, the second one.
No sir,
This one, left hand side, it also should be r e to the power minus half, not minus 1. Y is also there, no? V dV dy, 2V 1y, 1y both are r e to the power minus half, V is also r e to the power minus half, y is also r e to the power minus half. So, 1 r e to the power minus half gets cancelled. Okay. Right hand side here, the first term, even you have to say the order of nu, what is the magnitude of order of nu? U infinity L, U infinity L by R E, or U infinity L R e to the power minus 1. Okay. And then the other, U infinity, why U infinity square? U infinity by L square. Okay. And the last one, U infinity r e to the power half plus. Okay. So, here you see this, if you multiplying this, the first term is of the order of r e to the power minus 3 by 2, the other is r e to the power minus half. So, looking here, this term is r e to the power minus half, this is also r e to the power minus half, here one is r e to the power minus 3 by 2, other is r e to the power minus half. So, this term is of third order, r e to the power minus half cube. If r e to the power minus half itself is a small, it is cube of it. So, that is always negligible, there is no doubt about it. Okay. Come to the first term. The first term T is again of the order of u 0 by L, okay, or L by u 0. T is of the order of L by u 0. So, this dV dt, this term also has this type of order, u infinity square L r e to the power minus half. So, on the right hand left hand side, all three are of the order of r e to the power minus half, and the right hand side the largest term is r e to the power minus half. So, what it implies that this dP dy must be of the order of r e to the power minus half. Since all other terms in a equation is of the order of r e to the power minus half, the remaining term has to be of that order, otherwise there will be no balance. So, what it says that dP dy is of the order of r e to the power minus half. What is dP dy? Pressure, change in pressure or pressure gradient within the boundary layer. Third order term is still smaller. If r e to the power minus half itself is smaller, very small, then a cube of it is even smaller. So, that is so small that it can always be neglected. Now, in this case we have found that this equation simply gives us that pressure gradient within the boundary layer is of the order of R e to the power minus half or of the order of boundary layer thickness. It has also same smallness, pressure variation within the boundary layer has the same smallness as the boundary layer thickness itself. Now, once again considering the x momentum equation, you see in x momentum equation we have neglected all term which are of the order of R e to the power minus half. In the x momentum equation we have not retained any term which is of the order of R e to the power minus half, neither in the continuity equation. Only those terms which are of the order of u by L, they are retained. Okay. So, since we have retained only those terms which are of the order of u infinity by L in the x momentum equation, it is justified that here also we retain only those terms which are of the order of u infinity by L, but there is no such term in y momentum equation. That means, the complete y momentum equation can be ignored, giving what? That dp dy equal to 0. So, if we want to have second order term, let us see, if we want to have second order accuracy, then in the x momentum equation still no change, the term which we have neglected, which that itself is second order. So, if we want second order accuracy, only one term was neglected in x momentum equation, if you remember, that due to u dx2. Even if you want second order accuracy, that term still can be neglected, but when you come to the y momentum equation, except this all other terms will remain if we want second order accuracy. If we want third order accuracy, then that term in the x momentum equation need to be included, that d to u dx2, while this term can still be neglected. So, only if we want a fourth order accuracy, no one has ever tried, then this term needs to be retained. Beyond second order, no other boundary layer theory exists as of now, either first order or second order. In most cases first order, in some special cases second order, but second order is only special, not classroom or regular study material as yet. So, what it gives this boundary layer theory? Another implication, that the pressure within the boundary layer remain constant, it does not change, meaning whatever is the pressure at the edge of the boundary layer or what we get from the inviscid flow solution, that itself is the pressure on the wall, that itself is the pressure on the wall. So, you see this pressure is now basically a known parameter. Once we have the inviscid flow solution, that incompressible irrotational flow solution, then the pressure is known. So, in the x momentum equation, the pressure term that is present is basically known. We will also see the experimental verification of these statements. Now, let us denote all parameters at the edge of the boundary layer, or which we found that by inviscid rotational flow on the surface. When we solve inviscid rotational flow, we still call that the values are on the surface, but basically they are not on the surface, they are at the edge of the boundary layer. Now, let us denote all those parameters which are at the edge of the boundary layer by a subscript E. Okay. Let us denote the velocity at the edge of the boundary layer is u e. U e p e. Now, let us satisfy x component of momentum equation at the edge of the boundary layer. Satisfy x component of momentum equation at the edge of the boundary layer. The first term d u e dt, second term u e d u e dx, third term what is V e? V e is 0. So, the third term is 0. Minus 1 by rho. Okay, we need not write even partial derivative here, because p does not change with y within the boundary layer, plus what nu d2 u e dy 2 is 0, because no further change in u e. So, these are related. If you consider steady flow, this is what is the your conventional Bernoulli's equation. This is what is the Bernoulli's equation, no? P plus half rho square equal to 0. So, solving a boundary layer equation now means what? We need to solve boundary layer flow what we need to solve? The equations are the continuity equation, these are the two equations that you have to solve subjected to the boundary condition. What are the boundary condition? We have no slip boundary condition on the wall, which is u equal to 0, v equal to 0 at y equal to 0 for all x, for all t. Anything? What else? At y equal to 0 delta u equal to u e. Okay. But we do not know what is say let us write it this way, u at any x, that is at any y at x t but we do not know delta. Take it this way, for very large y, anything else? Any other boundary condition? There is a very important thing, that this boundary layer flow is not distinct from the other flow. There is no genuine edge of the boundary layer. The boundary layer are the outer inviscid flow. They are the same and only one identity. They do not have a separate identity. So, they must merge very smoothly. The outer inviscid flow and the boundary layer flow smooth marginally, and for marge smoothing what do you need? That all the derivative at the interfaces must be equal, all the derivatives, first, second, third, fourth, as many as you want. Of course, we will not be able to satisfy all up to infinite boundary derivative. So, we will create some interface where might be some derivative discontinuous. If we make first derivative continuous, the second derivative can still be discontinuous, which means not smooth merging. So, how many we can make, that will determine our smoothness, the solution smoothness. but anyway what is required is that the derivative as you obtain it from two sides, from the boundary layer side and from the outer inviscid side is same. Or this may little confuse you. Let us write it this way and then finally we will write it. Let du dy at y equal to delta equal to dv dy, but this is at y equal to delta, this is equal to 0. Okay. And similarly, the second, third and all are can be written as 0. Actually, the required condition is that these two derivatives should be equal, and we know that these are 0. Okay. A smooth merging, for smooth merging of two layers, boundary layer and outer inviscid flow. These are the required condition for smooth merging of the two. In general, that is for any general, when there are two different thing and they merge smoothly, all the derivatives should be equal. In this special case, we know that these derivatives are 0. So, these are the equations that to be solved to solve the boundary layer flow and the outer inviscid flow, which we have discussed earlier, how to solve outer inviscid flow. Of course, there will be many more methods that will be discussed later on, but at least we have discussed some of the basic things. And once these two solutions are complete, we can say the flow solution is complete to some extent, not complete, but almost complete, because these two now, as you can see that this will affect the other, one will affect the other. As you see, this boundary layer solution obviously depends on the inviscid flow solution through this term. The inviscid solution comes in here. Okay. Similarly, once this viscous solution is going to affect the inviscid flow, So, there is an interaction. This interaction sometime may become weak, sometime may become strong, and if necessary this process has to be continued. Solve the inviscid flow, find the inviscid flow pressure distribution, use that inviscid flow pressure distribution to find the viscous flow solution. Once you find the viscous flow solutions, your boundary condition for the inviscid flow solution will change. So, recalculate your inviscid flow, obviously you are going to find a new pressure distribution, means a new boundary layer development until they converge. And once you get that, that is the complete solution within the framework of boundary layer hypothesis. However, all flows are not boundary layer flows, all viscous flows are not boundary layer flows, as we have mentioned earlier, that only for high Reynolds number that thing happen. And even there are certain cases when even at high Reynolds number there may not be a boundary layer flow. The boundary layer to develop, we need a opposition between convection and diffusion. Sometime they do not oppose. There are some flow situations where they do not oppose. In that case, there will be no boundary layer.